Hi guys, up to now we have seen the analysis of symmetrical faults. In case of symmetrical faults, we considered two faults. One was line to line to line fault, other was line to line to ground. We said that line to ground fault is a special case of line to line fault where ZF will be 0. In this we derived the fault current in PU was 1 by Z1 equivalent plus ZF in PU. Z1 equivalent was the equivalent positive sequence impedance of the system. Here S was 1 by Z1 equivalent plus ZF PU, or it was also equal to S base by mod Z1 equivalent plus ZF PU. This will be in MVA. This will be in PU. Okay, so this was the short circuit MVA. Here we also saw how to select circuit breaker. We saw two rating. One was the maximum momentary current, which we were taking 1.6 into I symmetrical. Other we saw the breaking current, in which we took speed factor into I symmetrical. But while calculating symmetrical RMS current, we will considering transient reactance of a motor and subtransient reactance of a alternator. And then we were multiplying it by an empirical factor corresponding to the speed of operation of the circuit breaker, whether it is a 5-cycle circuit breaker, 2-cycle or 3-cycle circuit breaker. So that is what we have covered in the symmetrical fault analysis. In this lecture we will be starting with the unsymmetrical faults. Now first of all, what are unsymmetrical faults? These faults are not symmetrical. Not symmetrical in the sense they will not be same across all the three phases. So which faults will lie in this category? Line to ground fault. Here only one line is grounded, other two are same. Line to line fault, two lines get short circuited and the third line remains as it is. And line to ground fault. Okay, two lines are shorted and grounded and third one remains as it is. Now here, as you can see from the name itself, I can observe that the conditions pertaining to all the three lines or conditions persisting in all the three lines are not identical. Hence, this will make the system unbalanced. And since it will make the system unbalanced, we will require the method of symmetrical components. In case of symmetrical faults, symmetrical components is not that much required because only positive sequence will exist. But here symmetrical components is very important because it will make the system unbalanced. Okay. One assumption that we will consider while solving the unsymmetrical fault is no load before the fault. As we saw in case of symmetrical fault, we analyze both the no load as well as the loaded conditions, but here we will only analyze the no load condition. So let us get started with our first fault, that is your line to ground fault. Now here what I have assumed is that the phase A gets grounded and phase B and C will remain same. Now before fault what will be happening? We are considering no load condition. If before fault current is 0, that is no load, IA is equal to IB is equal to IC equal to 0, and all the voltages, that is VA, VB and VC, all will be balanced. How come they are balanced? Because they will be equal to EMFs, and as I told you, all EMFs are only positive sequence. If no current is flowing, VT will be equal to EF and they will be balanced. Now once the fault occurs, what will happen? IA will be non-zero as current will be flowing into the fault, but IB and IC will still remain 0 because no load is connected at B and C phase. And VA will become equal to IA into ZF. Just by KVL I am writing, here current IA is going into the fault, so the voltage will be IA into ZF. Okay. and VB and VC will be unknown. So let us first analyze the components for the phase current. Okay. To know the configuration of the equivalent circuit, we must know the symmetrical components of current. So how to derive the symmetrical component in the currents? So we will find out IA0, IA1 and IA2. This will be equal to 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha. Current will be IA, IB is 0 and IC is also 0. Now from this matrix, IA0 will be equal to IA by 3. Similarly, IA1 will be equal to IA by 3, which is also equal to IA2. Okay, because IB and IC are 0. Now from here I can directly observe that all three sequence currents are same. Since current is only same in case of a series connection, so here sequence network will be connected in series. Okay. Earlier when we were studying sequence networks, then I told you we have to design separate sequence network for positive, negative as well as zero sequence. Now how those three networks will be connected together? They will be connected in series since the current through each network is identical. So how will my equivalent circuit look like? In case of positive sequence, we will show EMF as well as the equivalent impedance, because induced EMF is always positive sequence. In negative and zero sequence, there is no induced EMF, so only impedance is shown, Z2, Z0. And neutral impedance appears as 3 times the neutral impedance in the zero sequence circuit. We have connected it all together. Now, VA was equal to IA into ZF, which is equal to IA will be equal to 3 IA1 into ZF or IA1 into 3ZF. That is why the fault impedance is shown as 3ZF, because the current flowing in the circuit is IA1, IA2 and IA0, which are all equal. So in terms of IA1, IA2 and IA0, the impedance offered to the current is 3 times ZF. So the fault impedance will also appear as 3ZF and the neutral impedance will appear as 3ZN. Now from this circuit, if we derive the sequence current IA1, it will be EMF upon total impedance. Impedance is Z1 plus Z2 plus Z0 plus 3ZN plus 3ZF. This is the positive sequence current flowing in the circuit. Now fault current is equal to current of phase A, which is equal to 3 times IA1, which is equal to 3 EA upon Z1 plus Z2 plus Z0 plus 3ZN plus 3ZF. Okay. This will be the fault current going into the fault at the phase A. Now, if we wish to find how much power is being transferred to the fault, that will be called as short circuit MVA. Now, in symmetrical component, what is the power? 3 times EA1, IA1 conjugate, EA2, IA2 conjugate, plus EA0, IA0 conjugate. Now since there is no EMF induced in negative and zero sequence, so this will be 0. So power will be actually 3 EA1, IA1 conjugate. Now this will be 3 times EA1 will be EA, IA1 is EA upon Z1 plus Z2 plus Z0 plus 3ZN plus 3ZF. Now EA into EA conjugate will be 3 into mod EA square by, if we talk about mod S, it will be mod Z1 plus Z2 plus Z0 plus 3Zn plus 3ZF. Now if we wish to calculate this value in PU, I told you that we are assuming the no load condition before the fault occurrence. So no load condition signifies that induced EMF is equal to terminal voltage, which is equal to 1 angle 0. So S will be equal to 3 by mod Z1 plus Z2 plus Z0 plus 3Zn plus 3ZF in PU. This will be the short circuit MVA. If we wish to calculate this value in actual values, that is the MVA, so this value is in PU, it will be 3 into S base 3 phase by mod Z1 plus Z2 plus Z0 3Zn 3ZF in PU. This value will come out to be in MVA. So this is your short circuit MVA for the case of a line to ground fault. Now the most common mistake is this. Many people will forget this factor of 3 while evaluating the fault current or evaluating the short circuit MVA. So remember, this fault is different from a symmetrical fault as there is an additional factor of 3 in the numerator. Do not forget to consider this factor. The next fault that comes is line to line fault. So here what I have done is I have shorted the B and C phase with a fault impedance ZF. So ZF is my fault impedance and A phase is left as it is. Now since we are considering no load condition prior to the fault, that means IA, IB and IC were 0 before the fault. Okay. Now before the fault voltages would be equal to EMFs, which is balanced. What happens when the fault occurs? When the fault occurs, since fault is occurring in B and C phase, the A phase will remain as it is. So IA will remain 0. But if we apply KCL here, IB is there, IC is there, IC will be equal to minus IB. And if we apply KVL between these two, VB minus VC will be equal to IF into ZF, or we can say IB into ZF. So these all equations we can derive from the network that is given to us. But our objective while analyzing the unsymmetrical faults is to derive the connection of the sequence networks. That is how positive, negative and zero sequence networks are connected together. That we have to figure out while analyzing the unsymmetrical fault. For that we must derive the sequence component of the fault current. Okay. So here we have to derive IA0, IA1 and IA2. This will be equal to 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha. IA is 0, IB is equal to IB, IC is equal to minus IB. Now from here if we calculate IA0, it will be 1 by 3, 0 plus IB minus IB, that is equal to 0. So 0 sequence current is 0. Hence 0 sequence circuit will be open circuited. So remember, whenever the ground is not present, that is in case of a line to line fault, what will happen is that the 0 sequence circuit will be open circuited or 0 sequence current will be 0. What about IA1? It will be 1 by 3, 0 plus alpha IB minus alpha square IB. That is IB by 3 alpha minus alpha square. Now alpha was equal to 1 angle 120. Alpha square is 1 angle minus 120. Now the resultant of these two will be how much? when two equal phasors are oriented at 120 degrees with respect to each other, the resultant will be, how much will it come out if we calculate from the phasor? It will be j by root 3 IB. Okay, because this resultant will be root 3 and it will become j by root 3 into IB. So this is my IA1. Now if we calculate IA2, it will be 1 by 3 0 plus alpha square IB minus alpha IB. So that is equal to IB by 3 alpha minus alpha square. That is equal to minus j by root 3 IB. Now, as you can observe here, IA2 is equal to minus of IA1. Okay, that, and here in this circuit was IC is equal to minus IB. So that means the connection of positive and negative sequence will be similar to the connection of B and C phase in this fault, because similar kind of relation we are obtaining for the sequence current. But if you see here, VB and VC have an impedance of ZF in between them. But we still do not know what will be the impedance between the positive and the negative sequence network. To determine that, we need sequence component of voltages. So to determine sequence component of voltages, VA0, VA1, VA2 will be equal to 1 by 3 1 1 1 1 alpha alpha square 1 alpha square alpha. Now VA is unknown, let us leave it as VA. VB is equal to VB, but VC is equal to VB minus IB into ZF. Okay, by KVL. So now if we wish to calculate VA1, VA1 will be 1 by 3 VA plus alpha VB plus alpha square VB minus alpha square IB ZF. And VA2 will be 1 by 3 VA plus alpha square VB plus alpha VB minus alpha IB ZF. Now to determine the impedance connected between positive and the negative sequence network, here this sort of relationship we had between VC and VB, so we have to subtract the voltages. So let me take VA1 minus VA2. Okay, so if we take VA1 minus VA2, this VA term will get cancelled out, alpha VB will get cancelled out, alpha square VB will get cancelled out. What will remain is 1 by 3 alpha minus alpha square IB ZF. Now alpha minus alpha square we just computed, it was equal to j root 3. So it will be equal to j by root 3 IB ZF. J by root 3 into IB was equal to IB1. So actually the relationship that is coming between VA1 and VA2 has the same impedance ZF in between the two networks. So how will my sequence network will look like? This one is my positive sequence. This one is your negative sequence. Here we haven't connected the zero sequence because zero sequence current is 0. Hence the zero sequence circuit is open circuited. And the impedance connected between the two networks is ZF. Now if you see here, IA1 is the positive sequence current and IA2 is the negative sequence current. This entire voltage will be VA1. This voltage will be VA2. So VA1 minus VA2 will be equal to IA1 into ZF as we derived here. So this will be actually IA1 because j by root 3 into IB was IA1. So IA1 into ZF, that is what we derived in the previous case. Okay. Just now we derived that VA1 minus VA2 should be equal to IA1 into ZF, and that can be derived from this circuit also. And this here is your reference bus. As you can see here also, the EMF only appears in the positive sequence circuit. No EMF is induced in the negative sequence. From this circuit, if we wish to calculate IA1, it will be EA by Z1 plus Z2 plus ZF. This is IA1. Now fault current, which is equal to IB, it is equal to minus J root 3 IA1, because IA1 was J by root 3 IB. So it will be minus J root 3 EA by Z1 plus Z2 plus ZF. So this will be the fault current in the system when a line to line fault occurs. And now if we wish to calculate the power that is being transferred to the fault, we will compute short circuit MVA. As I just told you, in three phase symmetrical component, short circuit MVA is this. IA2 conjugate plus EA0 IA0 conjugate. Now we know that no EMF is induced in negative and zero sequence, so it will be equal to 3 EA1 IA1 conjugate, that is equal to 3 EA1 into EA1 conjugate by Z1 plus Z2 plus ZF conjugate, that is equal to 3 into mod EA1 square by Z1 plus Z2 plus ZF conjugate. Now if we wish to calculate magnitude only, it will be 3 mod EA1 square upon mod Z1 plus Z2 plus ZF. In PU it will be equal to 3, because EA1 will be 1 PU, mod Z1 plus Z2 plus ZF in PU. In actual values it will be 3 into S base 3 phase by mod Z1 plus Z2 plus ZF in PU. This whole value will be in MVA, whereas this value will be in PU. So this is how we calculate the short circuit MVA for a line to line fault. Okay. So remember here that the short circuit MVA also consists of a term 3 in case of unsymmetrical fault. Okay. There it was only 1 by Z1. The next fault that comes is double line to ground fault or line to ground fault. Here what we have done is we have shorted B and C phase and then we have connected it to ground by a fault impedance ZF. Now again here first we will consider the before fault condition. Before fault there was no load on the system. So IA is equal to IB is equal to IC equal to 0. VA, VB, VC are all balanced. Now when the fault occurs, what will happen is, since A phase is unaffected, it will remain 0, but here IB and IC will not be equal to 0, and here the fault current, the current going into the ground, is equal to actually IB plus IC. Since B and C phase are shorted, VB will be equal to VC, whereas VA will be unknown. Okay, and VB is equal to VC, and VB is equal to VC is equal to how much? IF into ZF, which is equal to IB plus IC into ZF, or what I can write is IA plus IB plus IC into ZF, because IA is 0 anyways, and we know the sum of the three currents is equal to 3 IA0 into ZF. So this will be the voltage of the faulty phase, that is VB and VC, that is equal to 3 IA0 into ZF. Now to derive what is the connection of the sequence networks for a double line to ground fault, we will derive the symmetrical component of currents. So to derive symmetrical component of currents, we will calculate IA0, IA1, IA2, which is equal to 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha. Here the current will be IA0 is IA is 0, IB and IC. Now if we calculate IA0, it is equal to 1 by 3 IB plus IC. IA1 will be equal to 1 by 3 alpha IB plus alpha square IC. IA2 will be equal to 1 by 3 alpha square IB plus alpha IC. Okay. So this will be your sequence component of the fault current. And here, since the fault current IF is equal to IB plus IC, it will be equal to 3 times IA0. So whenever in case of a double line to ground fault, you have been asked about the fault current, you will calculate 3 times the zero sequence current. But still from here it is not very clear as to what will be the connection of sequence network. And from here I can observe one more fact is, since IA is 0, what will happen is IA0 plus IA1 plus IA2 must be 0. That is, these currents should be like this: IA0, IA1, then IA2. So somehow the sequence network should be connected like this, so that all the currents are converging to the same point and their sum will become 0. So this gives us a hint of what should be the connection of the sequence network. To be more clear what is the connection of the sequence networks, we will derive the sequence component of voltages. To derive sequence component of voltages, what we will take is VA0, VA1, VA2 will be equal to 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha. VA is unknown, it is VA. VB is equal to VB. VC is also equal to VB. So VA0 is 1 by 3 VA plus 2 VB. VA1 will be equal to 1 by 3 VA plus alpha square VB plus alpha VB, or it can be written as 1 by 3 VA minus VB. How come VA minus VB? Because alpha plus alpha square is minus 1 because of this property. VA2 will be 1 by 3 VA plus alpha square VB plus alpha VB, which is equal to 1 by 3 VA minus VB. Now from here if you see, positive and the negative sequence voltages are equal. If these voltages are equal, then what will happen is these networks will be connected in parallel. But zero sequence and the positive negative sequence voltages are unequal. So to derive what is the voltage difference between them, what we will take is, we will just subtract VA0 and VA1. How much will this come out to be? 1 by 3. VA minus VA will get cancelled out, and 2 VB minus VB is 3 VB. So this will come out to be how much? It will come out to be VB, which is equal to IF into ZF, or we can say 3 IA0 ZF, or we can say IA0 into 3 ZF. Now based on the facts that we have derived in this sequence component of voltage and current, let us draw the sequence network. So here positive and negative sequence networks are connected in parallel because we derived VA1 is equal to VA2. But if you see here, current IA0 is flowing in the zero sequence network. By KCL, IA0 will flow here. So if we apply KVL, VA0 minus VA2 will be equal to 3 IA0 into ZF, because impedance is 3 ZF. That is what we derived in the last slide. that VA0 minus VA1 was 3IA0 into ZF. And VA1 and VA2 are identical, so VA0 minus VA2 should also be 3IA0 into ZF. So we will connect the impedance 3ZF between the 0 sequence and the positive negative sequence. So this is the equivalent circuit. And this here is my reference bus. Now to derive the fault current here, first we will calculate IA1. IA1 will be EA by Z1 plus Z2 parallel Z0 plus 3Zn plus 3ZF. Okay, this will be IA1, but we know fault current is equal to 3IA0. So to calculate IA0, what we will do is IA1 is going here, so it will get divided into minus IA2 and minus IA0. Why I am telling minus IA2 and minus IA0? Because the indicated direction of IA2 and IA0 are opposite to the actual current. So IA0 will be equal to minus IA1 into current division. Current division will be Z2 over Z2 plus Z0 plus 3Zn plus 3ZF. Okay, so this way we can calculate IA0, and then 3 times IA0 will yield the fault current. Okay, so this is the method of calculating the fault current in case of a double line to ground fault. But remember, in all these cases that whatever impedances we are taking, they should be in per unit. Okay, usually this analysis is done in PU. You can take in ohms, but then you have to remember that this EA represents the per phase voltage. Okay, so it is better that you solve it in PU, because that will simplify a whole lot of effort. Okay, and remember, fault current is 3 times IA0, and it is not related to IA1 directly. In line to ground fault, fault current was equal to 3 times IA1, and in double line to ground fault, it is 3 times IA0. Now to derive the short circuit MVA, or the power being transferred into the fault, again I am directly writing now 3 EA1 IA1 conjugate, because EA2 and EA0 are 0. That is 3 EA1. IA1 conjugate will be EA1 conjugate by Z1 plus Z2 plus Z2 parallel Z0 plus 3Zn plus 3ZF. Now EA1 into EA1 conjugate, it will be mod EA1 square by Z1 plus Z2 parallel Z0 plus 3Zn plus 3ZF. Okay, in PU if we calculate, it will be EA will be taken as 1 PU, because of no load condition EA will be equal to VT. Z1 plus Z2 parallel Z0 plus 3Zn plus 3ZF in PU. In MVA it will be 3 into S base 3 phase by mod Z1 plus Z2 parallel Z0 plus 3Zn plus 3ZF in PU. This will give the result in MVA. So this is my short circuit MVA for the case of double line to ground fault. Now if we compare the fault or the short circuit MVA, then what will happen is, in case of LG fault, what it was, 3 by Z1 plus Z2 plus Z0 plus 3 Zn plus 3 ZF. In case of LL, it was 3 by mod Z1 plus Z2 plus ZF. So there was no trace of Z0. In LLG, it is 3 by mod Z1 plus Z2 parallel with Z0 plus 3Zn plus 3ZF. Now if you see the denominator of all these three terms, in this Z1, Z2 and all the impedances are connected in series. So this impedance will be highest and this will be lowest. Okay, and in this case what will happen is, here we have only Z1, Z2 and ZF, and Z0 is not there, so this will be higher. And here if you see, Z2 is in parallel with this impedance. Now whenever you connect two impedances in parallel, the resultant is less than either of the value. That is, it will be less than Z2 as well as less than this value. So this value is actually less than Z1 plus Z2. So this value is least, and thus the LLG fault has the highest MVA. But if you consider the symmetrical fault, it was 1 by Z1, or we can say 3 by 3Z1. So it is actually maximum. Why maximum? Because Z0 will always be greater than Z1 Z2. Why? Because of the transmission line in the system. Whenever you will have transmission line, Z0 for a transmission line is actually 3 times the positive or the negative sequence impedance. Since Z0 is very high, that is why the symmetrical fault or a triple line fault will have the maximum short circuit MVA, because the denominator will be minimum. But now suppose I eliminate transmission line from the system. How? I can say that the fault is occurring at the terminals of generator. Then transmission line actually does not come into the picture. And as far as we know, for a generator, what happens is Z1 is greater than Z2 is greater than Z0. So Z0 is actually minimum. So this order will be reversed, and LG fault will be most severe, or it will have the maximum short circuit MVA. So remember, whenever the fault will occur in a transmission line, symmetrical fault is most severe. If the fault occurs at the terminals of generator, LG fault will be the most severe. So it is not universally true that the symmetrical faults are more severe as compared to unsymmetrical fault. Why is this happening? Because in case of transmission line, zero sequence impedance is highest, which will reduce the fault current. But if fault occurs before the transmission line, then zero sequence impedance does not come into play, and the fault current will be higher for the case of line to ground fault. So do remember this concept, so that if there is a statement that says that the triple line fault is the most severe fault, that is not universally true. It is false, because whenever the fault will occur at the generator, LG will be most severe. So let us summarize what we have covered in the fault analysis. Whatever faults we have seen is, we have seen 4 types of fault. One is the symmetrical, and the 3 types of unsymmetrical faults. Then what are the currents? Then sequence voltage. Then let us say short circuit MVA. Okay, first fault that we consider is LG fault. What was happening? IA1 was equal to IA2 was equal to IA0. All networks were in series. And here the sequence voltage VA was equal to VA1 plus VA2 plus VA0, which was equal to IA into ZF. And short circuit MVA was 3 by mod Z1 plus Z2 plus Z0 plus 3ZF plus 3Zn in PU. Okay, so just remember the short circuit MVA expression in case of PU. And fault current in this case was equal to 3 times IA0. That was for the case of LG fault. Now what will happen for the case of line to line fault? In case of line to line fault, we saw that the ground was missing. So IA0 is equal to 0, and IA1 plus IA2 was equal to 0. What happened to sequence voltages? VA1 is equal to VA2. Both were in parallel. What was happening to short circuit MVA? Mod Z1 plus Z2 plus ZF in PU. And what was the fault current? Fault current was equal to minus j root 3 into IA1. Then double line to ground fault. All networks were in parallel. So IA0 plus IA1 plus IA2 was equal to 0. What happened to voltages? VA1 was equal to VA2. Okay. Here actually VA1 was not equal to VA2. VA1 minus VA2 was IA1 into ZF, because ZF was the impedance between the two circuit. Here VA1 was equal to VA2 and VA0 minus VA1 was 3IA0 into ZF. And what happened to the short circuit MVA? The short circuit MVA for a double LG fault was 3 by mod Z1 plus Z2 parallel with Z0 plus 3Zn plus 3ZF in PU. What was the fault current? It was equal to 3 times IA0. So that is actually the line to ground fault. And what happened to the symmetrical fault? That is, we consider triple L fault. Sequence current only IA1 was non-zero. Negative sequence and zero sequence did not exist because it was a balanced fault. Okay. And here, in case of this, only VA1 was non-zero. Again, negative and zero sequence voltages were 0. What was the short circuit MVA? 1 upon mod Z1 in PU. And what was the fault current? It was equal to IA1 because only positive sequence was flowing in the system. So these are 4 type of faults that we have covered. Out of this, one is symmetrical and other 3 are unsymmetrical. What you have to remember in case of unsymmetrical faults is, you have to remember the fault current, short circuit MVA and the equivalent circuit of each of the fault. If you remember the equivalent circuit, most of the problems you can solve directly. And remember some salient features of each type of fault, like in a line-to-line fault, zero sequence current is 0. So whenever there is no ground in the fault, then zero sequence current cannot flow. So in case of ungrounded fault, zero sequence currents are always 0. Okay. In the next lecture, we will study about the importance of neutral grounding. Why is it important to ground the neutral to save the system from any damage? That we will cover in the next lecture.